Hello everyone. Today I'm going to show you how to do linear regression in RStudio. For this video, we're going to cover simple linear regression, multiple linear regression, regression with interactions, regression with powers, regression with categorical variables, and finally, we're going to cover testing the assumptions of the models. So for this video, we're going to use the following dataset. We have three columns: y, x1, and x2. So let's go to our RStudio first and import the data. To import the data, we can use the following code. So these three codes will create three lists of numbers: y, x1, and x2. And this code right here is going to combine those three lists of numbers as a data frame called df. And now if you look at df, it's going to be something like this. Alright, so now we're going to go and create our first model, which is the simple linear regression. For simple linear regression, we're going to use x1 as the explanatory variable. So let's go back to R. In order to create the simple linear regression model, we're just going to run this following code. So now we created the model. What we can do now is we're going to look at our model. So to look at our model, we should just run this code. So this is the summary of all our model. First, we have the estimates of the coefficients. So we have the intercept, or beta 0, as 12.045 and beta 1 as 2.521. So yeah, we already have the coefficients, but not only that, we actually have the p-values. So for beta 0, the p-value is 0.3418, and for beta 1, the p-value is 0.0485. Not only that, for this output, we also have the multiple r squared, adjusted r squared, and the f statistic of the model. Since it is a simple linear regression, the p-value of the f statistic is the same as the t statistic. Another way of creating the simple linear regression model is with this following code. So for this code, we're going to say that the y and x1 column comes from the data frame called df. So if you run this code, we're going to get the same thing as before. The difference is we're going to say that y and x1 actually comes from the data frame df. Next, we're going to jump into multiple linear regression. For multiple linear regression, we're going to have x1 and x2 as the explanatory variables. So if we go back to R, to create a multiple linear regression model, we should just run this following code. And here is the summary. Again, we have the estimates of the coefficients, the p-values, the r squareds, and the f statistic. Now, another way of creating the same model is to use this shortcut. So this bullet point basically represents the fact that we're going to use every other column other than y as the explanatory variable for the model. So if we run this code, we're going to get the same thing. So you can use this shortcut if you're going to use every other column in your data frame as the explanatory variable besides y. Alright, so that's it for multiple linear regression. Still very easy. So now we're going to get into linear regressions but with interactions. So this is going to be the formula for our model. So notice that we have this term, which is basically saying that x1 and x2 has an interaction that affects y. Alright, so how do we code this in R? So if you go back to R, for interactions itself, we only need to add this following sign between x1 and x2. So if we run this code and we look at the summary, we have the following results. So this sign basically means that x1 and x2 has an interaction. Now, other than that, we can also use the asterisk sign to indicate that x1 and x2 has an interaction. If we run the code, we're going to get the same thing. Now you can use this one, this code, and this code. It doesn't really matter. The results will be the same. Alright, now we're going to look at regression models with powers. So for this case, we're going to have x1, x2, and x1 squared as the explanatory variables. So if you go back to R, the way to do it is to have this line added to the code. If we run the following code, we get the following results. So this coefficient is the coefficient for x1 squared. Now if you don't really like the way this looks, we have another way. Another way of adding powers to the model is by first creating a new column. Let's say the column is named x1 squared as the square of the variable you want squared. So if we can run this code, and now we can create the model with the new column we just created, and the results will be the same. Personally, I find this way as quite annoying because we need to create a new column. Rather than that, I will just use this code right here. Okay, so that is it for powers. Oh, and by the way, this doesn't only apply to squares. It could apply to any powers. We could do cubes or even quadratics and other powers you want. Okay, so now we're going back to the slide. Now we're going to do regression with categorical variables. So for regression with categorical variables, we're going to add two new columns, cat1 and cat2. So cat1 has two levels, A and B, while cat2 has three levels, 1, 2, and 0. Keep in mind that 1, 2, and 0 are not numbers, but they are categories. Alright, so first let's go to R, and we're going to see how we're going to import the columns. So for cat1, we're going to import this column right here, and cat2 we're going to import this column right here. And now we're going to insert the column into the data frame, like with this code. And now, before we create the model, we need to declare that cat1 and cat2 are categorical variables. And to declare them as categorical variables, we need to run this following code. Remember, this following code is especially important for the cat2 column, since the cat2 column is in numerical form. We need to do this in order for it to recognize it as a factor or as a categorical variable. Alright, now to create the model, so we're going to create this model right here, which is basically x1, x2, and x3, where x3 equals to 1 if cat1 is equal to b, and 0 if it's not. So now, to create this model, we could just run this code right here. So now if we look at the summary, we have the following estimates. So minus 18.026 is actually just alpha 1 in this model. So now, what if we wanted cat1 equals to a when x3 is equal to 1 if cat1 is equal to a? What if we wanted something like this? Well, if we wanted something like this, we could just run this following code. So this code basically tells us that now we no longer want a as the reference, but we want b as the reference. So now if we run the code again, we're going to have this result. So now we have cat1a, which basically means that x3 will be 1 if cat1 is equal to a. So that is how you're going to manipulate the model that you want to create when it comes to categorical variables. Alright, next we're going to try and create a model with a categorical variables with 3 different levels. So if we go back here and we run this following model, we'll get the following results. Now, when it comes to a categorical variable with 3 different levels, we're going to have 2 different coefficients, alpha 1 and alpha 2. If we have k different levels, we're going to have k minus 1 different coefficients. Alright, so now we can do other stuff with categorical variables. Perhaps if you want to see an interaction between the categorical variables and the numerical variables, we can do it with the following code. So this code is basically saying that x1 and cat2 has an interaction. So again, to do this in R, we can just use the following code, which is saying that cat2 has an interaction with x1. So if we run it, we're going to get something like this. Now, another way of doing a regression with categorical variables is to create dummy variables. Now, to create dummy variables, first we're going to import the fast dummies library. So we're going to import it. Now, if you don't have this library, you can install it first by just pressing this button right here, install, and just finding the package that you want to install. So let's say fast dummies. There we go. You just press fast dummies and press install. Now, since I already have it in my computer, I won't press it, but if you haven't have fast dummies installed, you should install it definitely. Alright, after that, we're going to create a new data frame called df2, which basically is the df data frame, but we have cat1 and cat2 dummy variables, and we're going to remove the first dummy. Okay, so if we run this code, we created the new data frame df2. So now if we look at df2, we have y, x1, x2, x1 squared from before, cat1, cat2, cat1a, cat21, and cat22. So for cat1a itself, this basically means that this column is going to equal to 1 if cat1 is equal to a. If it's equal to b, it's going to be 0. Same goes for this column. So this column is equal to 1 if cat2 is equal to 1. And this column is equal to 0 for others. So since cat2, for this one, cat2 is equal to 2. So cat2 underscore 1 is equal to 0. Same thing goes for this one. So this one is cat2 underscore 2. So it's going to be 0 if it's not equal to 2. Alright. Remember, when creating a dummy, you need to remove the first dummy, because when creating the model, you're not going to use all of the dummies, you're only going to use k minus 1 of the dummies. And now we can just create this model, and which basically uses Wait a minute. So sorry, this needs to be A. Okay. Right. Okay, so now if you run it, now we get something like this. So this model is basically using every variable available in the data frame, but using dummy variables. Again, you can just use the following method if you want to, or you can use the dummy variable method. So that's it for regression with categorical variables. And now we're going to test the assumptions of the models. As you know, for linear regressions, there are 4 assumptions. We have the normality assumption, we have the multicollinearity assumption, the homoscedasticity assumption, and the autocorrelation assumption. So first, let's just try to do a hypothesis test to test whether or not the residuals are normally distributed or not. So if we go back to RR, so for our normality test, we're going to test whether or not our residuals comes from a normal distribution or not. So first, let's check out the residuals of our model. So to get the residuals, we should just run this following code. So for this example, we're going to use model 2, which is basically this model right here, as an example. Alright, so the residuals are something like this. And now, for the normality test, we're going to use the Shapiro-Wilk test. The reason I'm going to use this test at this tutorial is because it's the easiest one to interpret. For the Shapiro test, the null hypothesis is that the residuals come from a normal distribution, and the alternative is that it does not. So to do the Shapiro test, we could just run this following code to get this following result. So we see here the p-value is quite large, and if you're going to use an alpha of 0.05, then the null hypothesis is we fail to reject the null hypothesis. So we can conclude that the residuals come from a normal distribution. So that's the first assumption. Next, we're going to check for multicollinearity. So we obviously don't want to have multicollinearity in our model. And to check for multicollinearity, we're going to use the fifth factor or variance inflection factor to indicate whether or not there's multicollinearity or not. So usually we use, if the fifth value is less than 5, this indicates the absence of multicollinearity, but sometimes you can also use the value 5 less than 10 as an indicator of the absence of multicollinearity. So 5 or 10, you can use either one, but most of the time it's very good if you can show that your fifth value is less than 5. Alright, so the code for R has this. So first we need to import the library car. Remember, if you don't have it installed, you can just install it yourself. Then searching car and press install. Next, we're going to run this following code. So fifth and the name of the model. Now this is the output. So we have that x1 has a fifth value of 2.625 and x2 has the same value. Since both of these values are less than 5, we can conclude that there is no multicollinearity in the model. Alright. Next, we're going to test for homoscedasticity. So for homoscedasticity, we have the null hypothesis that the residuals have constant variance, or basically homoscedasticity, and we have the alternative that the residuals does not have constant variance, or heteroscedasticity. We obviously want our models to have the same variance or the constant variance. So now, to test it, we can use the NCV test, or the non-constant variance test with the null hypothesis that the residuals have constant variance. So if you run this code right here, we're going to get the following output. So for this output, we have that the p-value is 0.9. So 0.9 is greater than the 0.05. Therefore, we can conclude that the residuals is actually homoscedasticity, has homoscedasticity. Now, other than this test, we can also do the Bruch-Pagan test. So for the Bruch-Pagan test, we're going to first import the LM test library. After importing the library, we can do the Bruch-Pagan test with this code. Now the Bruch-Pagan test also gives the same conclusion, which is that the residuals have constant variance. Alright, now we're going to test for autocorrelation. So the null hypothesis is that the residuals are not correlated, and the alternative is that the residuals are correlated. Obviously, we don't want the residuals to be correlated. So now we're going to do the test. For the test, we're going to do the Durbin-Watson test. So the Durbin-Watson test comes from the CAR library. So if you already installed the CAR library from the multicollinearity test, then you're good to go. Now we're just going to run this code, and here is the output. So the p-value is again greater than 0.05. Therefore, we can conclude that there is no autocorrelation in the residuals. So now, after completing all those 4 tests, we can safely assume that our model, or the model with x1 and x2 as the explanatory variable, fulfills all the assumptions. So now we can use the model to predict. So let's try predicting the following data set. So we're going to predict y with x1 and x2 like this. Okay, so how are we going to do it? So first, let's create the data frame first. So x1 new, x2 new, and df new. So when we're going to use our model to predict the value, we need to make sure that the columns of the data frame we're going to predict has the same column name as the columns that we use to build the model. So since we have x1 and x2 as the name of the column used in building the model, the name of the columns used to predict needs to be the same. So we have x1 and x2 and x1 and x2 again. Alright, so now for the predictions, we can just run this code. After getting the predictions, here is the results. So these are the results of the prediction of the models with the value from the new data frame. Now not only that, but we can also predict with confidence intervals. So if you want to create a prediction interval with a prediction with a confidence interval of 0.99%, we can run this following code. So if you run it, we can see that the results is something like this. So this is the lower, and this is the upper bound, and this is the lower bound, and this is the 0.99 confidence interval level. If you want it to be a 95%, you should just change this value right here. And that's it for the tutorial for linear regression in RStudio. Hope you enjoyed the video. and please share if you find this video helpful. Thank you.